So this problem is inspired by problem 10.2, where you're trying to calculate the forces in a tire of a racing car. So in this problem, a mouse has made itself comfortable in the wheel of your car. Tomorrow morning, as you start your car to drive to school, obviously this is in a universe where COVID doesn't exist because we're actually going to school and to work. You accelerate your car with a constant rate, a, in the y direction. The mouse, upon realizing what's happening, tries to make its escape out the wheel by jumping out. Describe all the forces that the mouse feels as viewed from you in the car, and also describe all the forces the mouse feels as viewed from someone on the ground. Okay, so remember that the effective forces are going to be these real forces minus r at double dot and omega dot cross r and omega cross r and 2 omega cross VR. Okay, so as you're driving your car away, this thing's going to have an acceleration a in the y direction. And also, we're going to have, well, I guess I could draw it from the mouse. We're going to have some gravity acting on this mouse, right? So that will be the real force. This is going to be negative mg in the z-hat direction. So I'm looking for a qualitative answer here, just to understand exactly when do we use all these terms. Because most of the time, we're really only dealing with centrifugal force. Sometimes if we have some projectile or something like that, we're also dealing with the Coriolis force. But we really haven't looked at those other two forces, those other two fictitious forces. So in this case, as viewed from you in the car, so that means that you are standing here in the same frame as this accelerating wheel, right? So this wheel is obviously going around with this angular velocity omega, but you're accelerating in this frame. So in this case, for you, the effective forces are going to be this gravity minus, and so you're in the same accelerating frame as this car, so RF is going to be 0, but you're going to also be, but this wheel is also accelerating, and so this is going to have, as you're accelerating the car, this wheel rotation is going to be accelerating as well. And I should be putting that this is R here. So we're going to assume, say, that this wheel is moving without slipping, just as we always saw, in the other problems. And so if that's the case, then what we have is the velocity of the car is going to be omega cross R R cross omega. But the acceleration of the car, no. omega cross r, and the acceleration of the car is going to be this omega dot cross r. Okay? So we actually do have this accelerating car, and so this is going to be this tangential acceleration is actually going to be playing a role in this fictitious force this time. Now we have this thing going at some angular speed. So we have the centrifugal force. So this mouse is going to be stuck to the rim of this wheel. It's going to be, pulling out radially to the rim of this wheel. And because this mouse is running out with a velocity vr in the x direction, we'll also have that contribution. Okay? Now for me, who's standing on the ground, it's a very large wheel apparently, I'm standing on the ground. Compared to me, the fictitious forces are going to include the fact that this thing is accelerating. All right? So that's going to have this RF, which is going to be our acceleration. And then we're also going to have the fact that this wheel is speeding up, and we're going to have omega cross r, the centrifugal force, and this should be plus, and we'll have the Coriolis force. Okay. So in this case, because this car is speeding up, compared to me on the ground, you'll have this, you would be feeling this accelerating force, right? As you speed up your car, you feel more like pressure on your back caused by this, this acceleration. So you'd be feeling that force. The mouse would be feeling that force as well. But then this mouse is also, the wheel is starting to spin up. And so this mouse feels that tangential acceleration force. And then it'll have centrifugal force, and it'll also, but then as the mouse starts to run away, then it'll have some velocity, and so it'll have a Coriolis force. So this would be an instance where you actually have to take all the forces into account.